This is section 3.6, and the title of this section is called Functions. So what we're going to do is introduce the concept of a function and talk about how to find the domain and range for a function, and also talk about function notation and how to use it. Before we can talk about a function, let me switch the screen here. Before we can talk about a function, we need to talk about a broader concept of something called a relation. And a relation is defined as any pairing of elements of one set often called the set A, the inputs, with elements of another set. And often that other set is called set B. So it's just any pairing of elements of one set with elements of another set. And two features we often investigate for a relation are the domain and the range. The domain is the set of inputs or elements from the first set oftentimes these are the x values if we're talking about pairing x's and y's, but they don't need to be x values. That's just the set of the inputs. Missed a word there. So the set of inputs, elements from the first set, and if we're talking about x and y's, those are the x values. And then the range is the set of outputs, or elements from the second set. And oftentimes these are the y values if we're talking about pairing x's and y's. So we'll look at some examples of different ways functions can be described. One way a function can be described, or a relation can be described, is as an ordered pair, or a set of ordered pairs. So here, where we've got this set of ordered pairs, remember this would be like an x and a y pair. The x values are the inputs, the y's are the outputs. So for the domain and range for this relation, we'd say the domain is just the set of all the x values, or the set of all x coordinates, and we'd make it just a list. So we'd say 4 and -4 and 2 and 10. So it's just a list of the x values that show up in those pairs. And the range is just the list of y values. And we wouldn't list the 9 twice. So we'd say 9 and 3 and -5. And in these sets, the order doesn't make any difference. We're just making a list, so the order could be rearranged, certainly, and that would be fine. We just need a list of all the x values for the domain and a list of all the y values for the range. I'm going to put arrows on this graph to indicate that it continues in the direction that it seems to be going. If we have a graph of a relation here, then we want to be thinking about, for the domain, the set of all the x values. And here, there is no leftmost x value, and there's no rightmost x value. Every x value we can imagine is going to show up as one of the points on this graph. So the domain we would list as an interval. We'd say -infinity to infinity. And the pattern here is like leftmost x, and then rightmost x. And since there is no left or right end to this graph, everything would just be covered, so -infinity to infinity. The range, on the other hand, now we're focusing on y values, so we're looking up and down. The domain is left and right. And we want the lowest y to the highest y. There's no lower end to this graph, so we would say the lowest, we would want to put -infinity. but the graph doesn't go above 3 and it gets to 3. So the range would be negative infinity to 3. So we need to list those as intervals since all of the x values on this interval are included and all of the y values on that interval are included. So for a relation, there's absolutely no restriction on the pairing of the elements from one set with the elements of another. Then, to talk about a function, we add a restriction. So a function is a relation, so a pairing of elements of one set with elements of another, in which each input is paired with exactly one output. Another way of saying that is given an input, we know without question the output. So if someone tells us the input is 2, we can't say, oh, the output could be 4 or 7. We have to know it's exactly this value. Right? So again, we'll look at relations described a few different ways and try to decide which are functions and which are not. So let's look at these two that are described as sets of ordered pairs. If we're trying to decide if we have a function, we want to make sure that no input goes with more than one output. So clearly in B, we've got a problem because 1 is paired with 2, and it's also paired with 3, and it's also paired with 4, and it's also paired with 5. So we would say this is not a function. Input 1 paired with more than one output. But the first example, each of the inputs, 0, 2, -2, and 4, are only paired with one output. It's fine that -2 and 4 are paired with the same output. It's just a matter of watching to make sure that no input is paired with 2 or more different outputs. So this is a function. Each input is paired with only one output. If you have seen functions before and you remember, there's something about this when two inputs are paired with the same output. That's a different characteristic. That's called checking for whether a function is one-to-one. We're not worried here about this issue of different inputs going to the same output. That's something we'll worry about when we're worrying about finding the inverse for a function. So as long as each input is going to only one output, we're fine. So this is a function. It's not one-to-one, but we're not worried about that right now. Let's look at example C. This is our only example. That's just a kind of a verbal description. But if we think of the set of inputs as the people in our class, and the correspondence being the birth date, so this set of outputs being the set of dates, we want to decide if this is a function. So the question you want to ask yourself is, if someone gives you an input, so if someone names a person in our class, can we say, without question, here's the output? And we should be able to, and so we should say, yes, this is a function, since every person has only one birth date. Um, Again, it could be the case that two of us have the same birth date, but that's not a problem. That would mean that we don't have a one-to-one function, which is something we'll talk about later, but we still have a function because every person has only one birth date. The relations here in the second column, D, E, F, and G, are all described by an equation, right, relating x and y. When you have a relation described by an equation, to decide if it's a function, you want to try to solve for y. If you get a single expression, then y is a function of x, or the relation represents a function. So in each of these, D, E, and F, we can solve for y. Here we'd have 3y equals x minus 2, so y is 1/3 x minus 2. So we can solve for y just like that. But in G, we notice something is different. If I try to solve for y, I have positive or negative square root of 2x. This causes a problem because given an x, we don't know which y value we're supposed to have for the output. Would it be the positive square root or the negative square root? So because of this, this is not a function. Let's say inputs can have more than one output. Let's just say this, inputs have more than one output. Right? Like if x is 1, for example, y would be either square root of 2 or negative square root of 2. But in all of these examples, the relation represents a function. We can solve for y and get a single expression. That's the key. Not a positive or negative. Right? So in D and E and F, all of those are representing functions. And the idea is if you can solve for y and get a single expression, then that equation represents a function. Another standard test for functions is if we've got a graph of a function, we have a quick way to test, if we have a graph of a relation, we have a quick way to test if it's a function. And that is this. The vertical line test for functions states, if no vertical line can be drawn so that it intersects the graph more than once, then the graph is the graph of a function. Let's state that an equivalent way that just might be a little more useful. If any vertical line passes through the graph more than once, the graph does not represent a function. So if we scan through these graphs and see which seem to represent functions and which don't, certainly B fails the vertical line test, so this is not a function. And you can see why this test works. We're at a specific x value, and we've got two different y values that are paired with that same x, which means there are inputs that have more than one output. That means not a function. So, not a function, and the reason this fails the vertical line test. A, on the other hand, let's fill in this gap here. A seems to pass the vertical line test, so we would say this is the graph of a function. seems to pass the vertical line test. And then two more examples here to check. D clearly fails the vertical line test, so not a function. But C seems to pass it. Let's put arrows here. But if we continue in this way, and you can imagine that any linear function should be the graph of a function. So, or any linear equation, the graph will be a function as long as it's not a vertical line. In section 8.1, we'll investigate linear functions in more depth. So we'll make connections between what we were doing in the first part of chapter 3 and then this idea of a function. Now we'll look at function notation. What you're going to see is that instead of rewriting equations relating y and x with a y equals every time, we're going to replace those y's with function names. And the reason for that is, if we have a few different ways that x and y might be related, it's nice to name the pattern that's relating x and y rather than calling it y every time. So the f of x just names a pattern for relating inputs to outputs. And the standard names that are used are F and G and H, but you can use any letter you want to for the name of the pattern. The value sitting next to the function name is the value used for the input. So the standard input is X, but when we put a 3 next to that F, that's going to mean let's put a 3 into the pattern where the X is and see what we get. So we're going to substitute the value in parentheses for the X in the pattern. So we'll always substitute the value or the expression in parentheses for the X in the pattern. So the way we would read this, we would say f of 3, and that tells us we're going to put 3 where the x is in the pattern for f. So that's going to look like 2 times 3 plus 1, which we can calculate and get 7. And then if we were to graph that, what we're saying is that when x is 3, y is 7. So for the input 3, the output is 7. Let's look at the next one. So now it's saying use the pattern for G, but input -1 where the x is. Anytime you substitute a value for x, you need to put parentheses around it. So here we'd have the value -1 squared minus 4 times -1 plus 3, right? So we took this -1 and put it in for each of the x's in the pattern G. So that's going to give me 1 plus 4 plus 3, so 8. And again, we could write that as the ordered pair. When the x is -1, the y is 8. And then moving on to the pattern called H, if I want to use H, find H of -3, I'll substitute -3 for the x in pattern H. So it'll be 1 over -3 plus 5, so a half. And once more we can write the ordered pair. -3 is the input, and the output we calculated would be a half. And then G of 0 would be putting 0 in for x, and again using the pattern G. So we'd have 0 squared minus 4 times 0 plus 3, which gives us 3. So the ordered pair would be the x was 0 and the y, the output, is 3. Then, instead of putting numbers in for the x's, we can also substitute expressions or other variables. So if I want f of a, this would say put that a where the x is in the pattern. So instead of 2x plus 1, I'll have 2 times a plus 1. And h of t would be the same as this pattern, but with a t instead of the x. So 1 over t plus 5. Or we can even substitute a more complicated looking expression. If I want f of x plus h, I would substitute that whole expression where the x is in f. So 2 times, replace the x with x plus h plus 1. Right, so this whole group gets put in where the x is in the pattern for f. Similarly, g of x plus h means I'm going to take that x plus h and put it in for each of the x's in the pattern for g. So that's going to look like x plus h squared minus 4 x plus h plus 3. Right, so each of those x's I wrote in blue as the new group x plus h. Then we just need to simplify that, and we've got a binomial squared, so we can use that pattern. And then we would distribute the -4 and combine like terms if there were any, but you can see there aren't any like terms, so I can stop right there. I want to look at two functions that are so simple they can be confusing. One of them is called the identity function, and the notation just says f of x is x. The other is called a constant function, and this 5 could be replaced with any number, but g of x equals just some number. For f, this is just saying whatever the input is, the output is the same thing. So f of 4 would just be 4, and f of -1 would be -1, and f of a would just be a. So it's a very simple function that just takes the input and gives it back to us as the output. And g, if I want g of 4, that should just be 5. And similarly, if the input is -1, the output is 5. Or if the input is a, the output is 5. So we call it a constant function because the output stays the same no matter what the input is, right? All right, then a word, not a word problem yet. I'm just looking at a graph and doing some interpretation. So we've got the graph of a function here, y equals f of x, and we want to answer some questions about this graph. Let's assume each square is 1 by 1. And the first question is, what is the range of f? We'll have some more practice with range and domain from graphs on the next couple pages here, but for the range we always want to be looking up and down. We want the lowest y value to the highest y value. In this case it looks like the lowest is -2 and the highest is 2. So we would write this as an interval. We would write -2 to 2. And I'm choosing to put square brackets on those because it looks like we actually get to each of those values. We get as low as -2 and we get as high as 2. The domain, we want to look left and right and say what's the farthest left x, what's the farthest right x. And in this case it looks like we get as far left as -5 and as far right as 5. So we'll write -5 to 5, that whole interval. We don't want to write -5, -4, -3, -2, -1, and so on, because we actually get all the values between those two. So the only way to correctly write down this interval this domain or range would be to use interval notation. We can't list the points one by one. Then question C here asks, what is f of negative 2? So remember, the number in parentheses here is our x value. So we're looking for y when x is negative 2. So we go to where x is negative 2, find the y value at that point, and it looks like the y value is negative 1. So we would write f of negative 2 is negative 1. Then question D asks, in some sense, the opposite question. Find the x values, so we're looking for the x, such that the function or the output or the y value is negative 1. Right, so this is the same question. We want to know if the y is negative 1, find the x's. So I'm going to draw a line through where y is negative 1. And notice there are several x values that give us that y value. It looks like if x is negative 2 or 4, the y values would be negative 1. So we could put that in a set and list those are the x values that make that happen. Then these last two are just practice again, going back and forth between ordered pairs and function notation. You can check for yourself that the pair 5, 0 is actually on that graph. And the way we express that using function notation is that if the input is 5, the output is 0, or f of 5 is 0. And then the last question is just asking us to go the other way. If we know that f of negative 5 is 2, that would mean that the pair negative 5, 2 is on the graph. And then you can check that that's really the case. And certainly it is. Now we've just got a word problem using function notation. This is telling us that we've got a function that shows the number of passengers in millions aboard airline flights in the US, where the input is the number of years since 1991. So if I want to find and interpret P of 4, finding it is relatively easy as long as we have a calculator. We would say P of 4, taking x to be 4, would just be 25.4 times 4 plus 448.4. So grab a calculator, get that number. Looks like 550. And what that means is, since the output is measured in millions, 4 years after 1991, since X is years after 1991, there were 550 million passengers on airline flights in the US. So we would say in 1995, there were 550 million passengers on airline flights in the US. Right? Because again, this is years after 1991. And the output is measured in millions. And then, if this model holds for more than 1991 through 1997, we could predict maybe how many passengers there were in 2005. So in 2005, we would say, well, that's a year, so it's going to be X, how many years after 1991? It would be, what, 14? So we would say P of 14. We would put 14 in for X. And grab a calculator again. So 804, which means the model predicts 804 million passengers in 2005. So let's think about this function a little bit. This is linear because it's in the form mx plus b, right? So thinking about the stuff we learned earlier in chapter 3 here, the slope is 25.4, which means the number of passengers is going up by that many million per year, right? So the number of passengers is increasing by 25.4 million per year. And this 448 would be the value at the start, which in this case is 1991. So we could say in 1991 there were 448.4 million passengers. So it's good to make connections with what we've been learning in chapter 3 and what we're seeing right here. Finally, we've got a little more practice with just taking a graph and writing down the domain and the range for, some of these are not functions, but most of them are. So this is not a function. You can still talk about the domain and range for a relation, but I want to make sure that I don't sound like I'm calling that a function. Let's cross out these instructions. So find the domain and range of each relation. This one happens to be a function. This one's not a function, but let's write down the domain and range for each of these. So remember the domain, we're thinking x values, so we're thinking left, right. And the range, we're thinking y values, so we're thinking up and down. And you always want to write the smaller number on an interval first. So the domain on example A here seems to be as far left as -2 and as far right as 5. And for the range, it looks like it goes as low as 0 and as high as 5. And I put square brackets on all the endpoints because each of these values seem to actually be achieved. So square brackets. And again, domain, whether we're talking a function or relation, we want left, right, and range, we want the y values, which are up, down. So domain would be -3 to 3, and the range would be -4 to 4. C is again not a function, but it is a relation. So we can still talk about the domain and the range. The domain, we don't have a left end of the graph, but we do have a rightmost point, and that would be 1. Since there's no leftmost, we would say -infinity and then going all the way to 1. And it seems that the graph extends up and down indefinitely, so we would say the range would be -infinity to infinity. And D, we've got a line. We could probably figure out the equation for this line, but let's not worry about that right now. But just notice that it extends left and right without bound and also up and down without bound. So both the domain and the range will be -infinity to infinity. And that would be true of any line that's not horizontal or vertical, right? The domain and range would be all real numbers. And that's the end of that section.